Hey everyone, I'm Junhua Lu, PhD candidate at Purdue University, computer graphics major, and presenting our recent research outcome, Phoenix Map, an abstract approach to visualize 2D spatial distributions. Due to the conflicts between the limitation of display area and the large amount of comparative distributions need to visualize, the current methods are always restricted. These observations encourage us to come up with a solution by abstracting the visualization.
MetroSets is an online platform for visualizing sets as metro maps. In this style of drawing, sets are represented with metro lines, while the elements they contain are represented as stations. MetroSets is implemented using a modular 4-step pipeline, with a variety of choices for each step. The final visualization is interactive, with support for all common set operations. MetroSets is fully implemented and can be found at the displayed URL.
To uncover football tactics, we create spaces and times. We use time query, construct spaces, construct times. Our approach was used for reconstructing team tactics in different classes of game situation. Our domain experts are happy, and the Germans shall win again and again.
Designed in response to the COVID-19 pandemic, the novel visualization technique we are calling GOWNS accommodates continuously incoming and increasing case data without distorting past data. Layering linear scale graphs shows both small and large numbers. This allows more detail to be seen when scrubbing through time and comparing regions by realigning the GOWNS based on case numbers.
We study the limitations of node-link diagrams with respect to pathfinding tasks. But wait, I hear you say, hasn't that been studied before? Actually no. Past studies typically measure only accuracy and time for fixed network sizes. We used a number of physiological measures, including brain activity, and looked at a range of network sizes and densities. We discovered that the threshold for difficulty is much lower than expected. This talk is essential viewing for anyone interested in network visualization design.
Visual data analysis of large amounts of data demanded solution which provides users the means to enter into the dialogue with the information visualization. To understand how multimodal interaction using touch, speech, and middle hand gestures can tackle this gap, we conducted an explorative interaction elicitation study. We argue that users are highly receptive to use multimodal interaction for visual data analysis and that especially the combination of touch and speech would be promising due to their complementary nature.
We present an exploration into co-located collaborative immersive analytics in a prototype called Fiesta, the free-roaming immersive environment to support team-based analysis. The prototype allows groups of users to visualize and explore their data in a room-scale environment, which we used in an exploratory study involving 10 groups of 3 participants. We focus on the roles which 2D surfaces have, as well as how users leverage the 3D space during both the individual and collaborative work.
Although prior work has examined how visualization impacts decision-making, there is no concrete method for quantifying and comparing the impact of different encodings on decisions. We rethink how we evaluate decision-making with visualizations by leveraging work from economic theory. We present the results of a large-scale lottery game that evaluates the impact of 5 different visualization designs on risk behavior and decision-making.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Urban motion, illustrating the movement of population from billions of sparse trajectory records. Chang'an Avenue correlates with movement flow, the regions with the largest flow volume. Zoom into the region. The southern Huilongguan region is mostly in blue, cut by G6, which could account for its commuting issue. Rainstorm in Beijing, movement speed is much higher on average. At the remote regions of Beijing, there are few local movements.
Many real-world analysis environments involve multiple types of experts and analysts working together. We aim to provide new knowledge about the role of provenance in a variety of data analysis scenarios. We present the findings from interviews with data analysts from various domains. Our results demonstrate how different needs for provenance depend on different analyst roles and also helps to identify possible opportunities for advancements and new techniques for provenance support.
Do charts provide us with some kind of story? Or is it a message or some kind of insight? A lot of ambiguity involved here, right? We fix this by characterizing the visualization decoding process by providing a fact evidence framework to align the complexity of cognitive tasks and understand the chart interpretability process.
We propose V2V, a comprehensive pipeline for variable selection and translation for multivariate time-varying data. Our approach contains feature learning, translation graph construction, and variable selection. To demonstrate the effectiveness of our approach, we compare histogram matching, pixel to pixel, and cyclogram to evaluate variable translation. In addition, we also compare an information-aware framework to evaluate variable selection.
MeetQueues is an interactive visual platform which augments existing tools for meetings with features that help people engage and reflect. Its visualization shows if more people are satisfied or uncertain about the contents of a meeting. Attendees can add comments and upvote others' comments. Attendees can reflect on the contents and what happened during the meeting using the summary page sent after it is over.
The search for high prevalence of crimes ends up neglecting sites where certain types of crimes are frequent but not sufficiently intense to be considered statistically significant. In this paper, we proposed a technique centered on NMF to identify hotspots based not only on the intensity but also on the frequency. We introduced a visual analytic tool to support the domain expert in their analysis, whose usefulness of the system are highlighted by comparisons and case studies with real data.
Hello everybody, welcome to the next session It's a CG&A full paper session, so these are invited papers that have been presented beforehand in the journal. And the general title is VIS for the Masses, and I think we can expect 6 very interesting talks in this session. The first talk that will be given is about personalized sketch-based brushing and scatterplots by Chaoran Fan and Helwig Hauser, and the talk will be given by Chaoran Fan. So please welcome.
Hello everyone, welcome to my talk. I'm Chaoran Fan from University of Bergen. Today I'm going to present our paper, Personalized Sketch-Based Brushing in Scatterplots, which is co-authored with my supervisor, Helwig Hauser. Linking and brushing is very useful for interactive visual data exploration. Here is an example of linking and brushing. The brush view on the left shows a rectangular brush. The data is then highlighted in the linking view on the right. With linking and brushing, we can combine 3 different visualizations together. There are 2 criteria to judge whether a brushing tool is good or not. The first one is accuracy, which means whether the brushing interaction can lead to a selection that the user really wants. The picture shown here is a similarity brush, which is a typical example of sketch-based brushing. The user draws a polygon on the visualization, and the red curves are the brushing results based on the similarity function, which is designed behind. Mostly, this type of model-based brushing is not very accurate. The second criteria is efficiency, which means how fast is the interaction. Does it enable a fluid data exploration? For example here, lasso is very accurate, but it can be very slow, so it easily becomes a unique task by itself. In this paper, we want to develop a sketch-based brush in Scatterplots. It can be defined as estimating a function S, what the user wants to select based on the visualization and the interaction. Our goal is to make the selection S accurate and the interaction I fast. It is like the animation shown here. Our work is based on our previously published CNN-based brush in Scatterplots, which is inspired by the success of deep learning. To achieve this, we use the click and drag interaction, which is very fast. For training the CNN, we collected user study data from 50 users. To construct the input of CNN, we converted the interaction and the visualization information into an image. This method works quite well and achieves 97% accuracy. However, the CNN brush mentioned above was trained based on 50 users, which is a general model and may not be suitable for everyone. Of course, we can retrain a new model for a single user from scratch, but it is time-consuming and requires sufficient training data, which is difficult to get from a single user. These are our motivation to make a further improvement for the current solutions. Our core idea is to make use of the well-trained general model and adapt it step by step to a personalized model. Here is an illustration in 2D space. The red star is the general model, and we take advantage of it and adapt it step by step to a personalized model. In this way, the prior parameterization is taken into account, and we can get rid of the costly global search in the high-dimensional parameter space, largely reducing the time spent and making the results more stable. Our idea is based on two deep learning knowledge. The first one is a transfer learning, which allows us to bring the power of state-of-the-art models to new domains. For example, knowledge for recognizing cars could apply when trying to recognize trucks. The second one is active learning, which is a special case of semi-supervised machine learning that can incrementally improve the existing model by interactively querying the user for additional input. Here is our principal approach, which is an adaptive CNN-based brushing model. We offer an interactive scenario to improve the brushing accuracy for single analysis during data exploration. The user can actively give new input when the result generated by the current brushing model is not good. We can see the picture here. The original model is constructed based on the data from 50 users. When a new user uses this brushing tool, he or she can actively give new input to replace the old data. Then the user can choose to fine-tune the old model to a new one in a short time. This procedure can be repeated, and the model is getting closer and closer to a single user model while using it. Here is the information about how we replace the old training dataset. We compute the features of the input regarding goal size, area size, geometric shape, and the scaggnostics. Then we collect this information to formulate a similarity function. The most similar old data will be replaced by the new data. For retraining the model, the effective way for fine-tuning the pre-trained parameter is to make the learning process happen only in the fully connected layers and keep parameter of convolutional layers frozen. Besides, as we expect the weight of the pre-trained CNN is relatively good, and we don't want to distort them too much and too quickly. So the learning rate was set to be half of the learning rate for training the initial model, and we only need 2,000 epochs instead of 10,000 to obtain a good convergency. For the user study, we have 8 users and 25 new datasets were provided. Each user to participate for 5 rounds, and each scatterplot from 25 datasets show up twice in total, but in different rounds. For each round, one user needed to finish 5 selections in every 10 different scatterplots. These data are then applied to retrain a new brushing model, which is used for the next round. Here is a pipeline of the user study. A scatterplot was provided to the users, and then they can use the click and drag interaction to brush some data subset of their choice. The brushing result based on the current CNN model was shown to the users. If the results were not what they wanted, they could use a lasso to do corrections. The animation here shows the example of the user study. For evaluating our proposed iterative model, we did a quantitative accuracy comparison with the previously published general model. Here shows a box plot of the brushing accuracy over rounds based on the general model and our iterative model, respectively. In the first round of the user study, the user's brushing results are computed by the general model without optimization based on the new data. So the difference between the general model and our iterative model appears from the second round to the fifth round. The dashed line in the box is a mean. If we compare the accuracy by pairs in terms of the round, we can see after iterative retraining, our model performs better than the general one, with higher median and mean. Besides, the size of the box on the right are smaller than the corresponding one on the left. This indicates our model has less variance and becomes more stable. Statistically, with the retraining procedure over time, the results show a clear ascendant trend than the general model. Here is a line plot of the brushing accuracy over 5 rounds of 8 users based on the general model and our iterative model. By looking at the accuracy variation together, we can obviously see a rising trend of the accuracy over rounds on the right side, while the accuracy of the general model is more distributed on the left. This shows a strong indication that with additional data for retraining the model, it is able to gradually learn the brushing preference of a single user. In conclusion, we have achieved a solution which is able to turn the general model to a tailored model for a specific user, with a very short time training course, which is 3 minutes. We hope that this work can inspire further related research, especially in visualization, to make use of deep learning knowledge to improve the data-driven approach. Thanks for your attention, and I would like to answer questions if you may have.
Oh, thank you for this nice talk. And we already have the first question here. And this is about, are there any savings for this approach? Having to provide personalized data with periodic updates in your case, it seems like it would introduce more time delay than, for instance, in refining a lasso selection.
Welcome to our talk about aggregated ensemble views for deepwater asteroid impact simulation.
So the Zoom is muted, so we cannot hear what you're saying.
Oh, sorry, and can you hear my voice?
Now it's good.
Oh, yeah. And the main motivation for this iterative model is to help the user to improve the brushing accuracy while using this. Of course, it will take some time. It's and the retraining time mentioned is 3 minutes. And if it's not accurate enough, and you can also use the lasso to do the further correction. And we assume it will reduce the time that you use the lasso to do the correction compared with the general model. Yeah.
Okay, here is a follow-up question, also coming from Michael Corral. He is also curious about what specific tasks the participants had to do in the study and whether these specific subsets of points were told to care about.
Yeah, I think this is a very nice question. And during the task, and we give some hints to the user. We ask the user to select a small cluster or big cluster and the elongated cluster. And also the user can freely to select other subsets and they want. Yeah, and for the data sets, and we collect from the real data set, and we try to cover a good range of the characteristic of the data set, and we have different data sets provided.
So how transferable are these patterns that you can observe for one user when he gets different data sets?
Yeah, this is why we need this iterative model because different users, they have a different perception about what's the goal of their brushing. So,
okay,
yeah.
Thank you. Very interesting work, and I'm curious to see what is coming next, which interaction you will automate or improve.
Okay, thanks a lot. Yeah.
Okay. So the next talk will be about illustrating changes in time series data with data video by Junhua Lu, Wang, Huiye, Yuhui Gu, Zhiyu Ding, Mingliang, and Chen. I hope I didn't completely mispronounce all these names, but the talk will be given by Junhua Lu. So please start the video.
Welcome to our talk about aggregated ensemble views for deep-water asteroid impact simulations. My name is Leistikow, and together with Karim Huesmann, we are going to present an application for analysis of spatial-temporal multi-field ensembles. In particular, we target the analysis of deep-water asteroid impact simulations as it was given for the VIS contest 2018. A simulation was performed by varying three parameters, namely asteroid radius, the incoming angle, and the height of the airburst, if one was simulated. The resulting ensemble consists of 7 simulation runs with up to 500 adaptive time steps each. For each time step, the pressure and temperature field, as well as volume fraction of water and asteroid, is provided on a 300 by 300 by 300 grid. To give an example, we show a volume rendering of both volume fraction of water and asteroid separately and combined in a multi-volume rendering. In general, such an ensemble might easily contain more than 7 runs. For such ensembles, we want to detect spatial-temporal patterns, compare multiple runs, and analyze the influence of simulation parameters. Considering these goals, we propose a top-down analysis approach which should enable domain experts to efficiently grasp meaning out of their data. We start generating overview visualizations, aggregating data from the ensemble. We make use of function plots and similarity plots. Using a Monte Carlo sampling within the common domain of all simulations, we create a feature vector representing the sampled field, which drastically reduces the amount of data to be considered. In order to provide the first overview of the entire ensemble and its evolution over time, we use function plots, one of which can be seen here. Function plots are generated for each scalar field individually, aggregating information of all runs or a subset thereof. Basically, each component of the feature vector will be traced over time. By drawing a piecewise linear curve, you can imagine a sort of timeline. To demonstrate how the piecewise linear curves are generated, we look at this example. For each sample, we know the corresponding field's value at each discrete time step of each simulation. The control points of the lines, therefore, are calculated according to the actual time deltas between consecutive time steps. Between them, we use linear interpolation to create the segments. Here we see the evolution of one sample. Applying that technique on each sample increases the density each time an intersection or overlap occurs to happen. Thus, we effectively generate a 2D density histogram. Optionally, a logarithmic scale can be used for the density values which eventually are mapped to colors. In order to compare the evolution of all simulation runs and to analyze the impact of simulation parameters, we generate multi-run similarity plots. Each run is represented by a timeline, such that Euclidean distances between time steps encode similarity between respective scalar fields. Isosurfaces are an effective field descriptor and can capture the simulation states of the runs at each point in time. If a single isosurface describes the volumetric field well, we can use an isosurface similarity measure to compare two fields. To compare two isosurfaces A and B, we consider the intersection and union of their enclosed volumes to calculate the Jacquard distance. Since a single isosurface might not describe well the general behavior of a field, the use of multiple isosurfaces can be considered. When concatenating all enclosed volumes, the Jacquard distance can still be applied. However, manually choosing multiple ISO values is undesired. To solve this, the isosurface similarity can be generalized to a field similarity when assuming infinitely many isocontours. In this example, a 1D parameterization of two scalar fields is shown. The x-axis depicts the samples of the scalar field and the y-axis the respective field values. The intersection of all isocontours of two scalar fields A and B, shown in green, is then defined by the minimum of both function values. Similarly, the maximum of both function values can be interpreted as their union. The Jacquard distance can then be adapted accordingly. Calculating the pairwise Jacquard distances between all time steps of all runs, we generate a distance matrix which we use as input for multidimensional scaling, a distance-preserving embedding technique. In order to visualize the embedding, we aim to reduce the number of principal components. The eigenvalue analysis of the resulting principal components reveals that using the first three is sufficient. Making use of the presented overview visualizations, interesting patterns might become apparent. To analyze those patterns in more detail, we provide different detailed representations for a single time step. We provide single and multi-volume renderings for up to 4 scalar fields that can be rendered using their respective transfer functions. A quite common yet powerful tool for volume data exploration is the slice view. In this case, we choose the slice to be right above the water surface to be able to find water waves. The color encodes the volume fraction water, pure white means 100% water. The spatial similarity may be visualized using a volume rendering by computing the difference between either two volumes or between a volume and a group of volumes. All methods are integrated in an interactive application with coordinated views. On top, we can see both overview visualizations, below we find the detailed representations. All common properties like time, selected scalar field, or selected simulation run are linked between all views, such that an interaction in one view immediately affects all the others.
Having introduced our approach, we will apply the presented techniques on the deep water impact simulation ensemble. We start our analysis by looking at the function plot and the 1D similarity plot of the temperature scalar field of all runs. We can immediately locate the common main events of the simulations at the beginning, which was identified to be the impact or airburst of the asteroid. If we look at the function plot, we see that all runs show a sudden increase in temperature at the beginning of the simulation. This also becomes clear in the similarity plot, since it also shows large changes in the scalar field at the beginning of the simulation. The other scalar fields shows a similar pattern. Also, the two plots show the relaxation of the scalar fields back to their initial state. Some runs don't show this pattern, which is due to the fact that they were aborted in advance, so they didn't have time to reach their initial state. Furthermore, in the similarity plot we can see how the simulation parameters influence the development of the scalar fields. We can identify three groups with a similar change over time. The first group consists of the small asteroids, the second group of the directly impacting big asteroids, and the third group of the airbursting big asteroids. We now want to focus on this observation and take a closer look. First, we choose a time step where groups are quite separated from each other. We see the similarity plot of the scalar field containing volume fraction water. The plot indicates that all members of group 1 should look similar, in particular showing no changes in the observed scalar field. Comparing all volume renderings, here the red run, the blue run, and the purple run confirms this hypothesis. The chosen scalar field looks identical throughout the whole simulation for this group. The yellow and green timelines form the second group. We expect the two members of the second group to look more similar to each other than to any member of any other group, but also different to each other, which again can be confirmed. Using the same arguments as before, we expect the volume renderings for the third group to look mostly identical, which is not the case. The first principal component of our embedding seems to be perfectly aligned, but taking the first three principal components into account reveals their difference. When exploring the pressure scalar field, we discover an interesting pattern in its respective similarity plot, namely an oscillation. Here, an oscillation indicates a return close to the field's original state over and over again. A similar pattern can also be observed in the respective function plot. To see what is actually causing this kind of oscillation, we switch to the volume rendering of the yellow run, showing a mostly undamped oscillation. The oscillating pattern seems to be caused by the pressure waves reflecting at the simulation boundary, seemingly being a simulation artifact. Before, we already looked at the similarity plot of the volume fraction water scalar field. But comparing the plot with our expectations as far as the simulation parameters are concerned, we notice that simulation YA11, here shown in red, seems to behave differently than expected. The plot shows no noticeable change at all, but the parameters imply a direct water impact which would always result in any kind of water movement. Switching to the volume rendering reveals that neither the asteroid nor scattered particles ever get in contact with the water surface. The red simulation is YA11 and is shown here the closest it ever gets to the water surface. For comparison, the green simulation shows YA31, which impacts the water surface as expected. A dialogue with the simulation engineers revealed that YA11 was programmed to impact directly but airbursted due to physical constraints. In this work, we presented a visual approach in order to analyze spatial-temporal ensemble datasets. We proposed a structured exploratory analysis and allow for targeted queries at multiple aggregation levels. Applying these techniques to the deep-water asteroid impact dataset, we detected a main event to be the airburst or impact, visualized relaxation of the given scalar field, identified the asteroid size to be the most relevant simulation parameter, and discovered some unexpected simulation artifacts. Thank you for your time, and we're happy to take your questions.
So thank you for the interesting talk. Certainly a very challenging data set. I have a question here. So now you always showed kind of 4 or 5 different ensemble members. How does this approach scale with an increasing number of ensemble members?
We tried this approach on several different ensembles. We last time we used an ensemble with about 150 members, and this similarity plot really showed us how similar these runs are. So it really scaled very well. For the function plot, I don't know. We have not used it for these big datasets yet.
So did you think about using a clustering approach to find automatically which ensemble members are similar?
Well, so for the dataset we only got like 7 runs, right? And for those, the clustering was not necessary.
Okay, yes, you're right.
So we didn't apply that. But yeah, of course, like if you would have multiple or a lot more members, like 100 or more, then you wouldn't get around introducing clustering methods, of course. But of course, you could also, because like in the similarity plot, like mostly if there are a lot of groups, you could make a subselection and create a new embedding for the subselection, and maybe that also helps like figuring out how the different members behave. But yeah, clustering could be useful for a lot of members.
Okay. So I have a last question, which might be a little bit provocative. It's in the long run, how important do you think is actually the volumetric representation? Isn't it then probably the statistics that is much more important?
Like which volumetric representation are
the volume rendering. I think, do people really look at it? So you had one example that was nicely shown that you could learn something out of it, but in the long run, is it really so important?
Yeah, that's a good question. So in the end, like we presented a top-down approach basically, like of course, it depends on how many simulations you actually generate. If, for example, you target to generate only like 5 simulations with with highly varying parameters, then you might actually be interested in how the actual output in the volume rendering looks, to see like where do the changes come from. But if you have, for example, 100, then you maybe are only interested in what parameters, because you somewhat need to create the mapping between the parameters and the visual output, like how to interpret the result, right? And only looking at the overview visualizations, only looking at the graphs, you can't really interpret very easily without looking at the parameter configuration, what the asteroid looked like, and that makes somewhat the interpretation easier, I'd say. But of course, it's only one tiny, one element of the analysis toolbox, let's say.
So, thank you again for this interesting talk, and sorry that then I announced your talk wrongly, because I was already one step further in my plan here. But so interesting talk. Thank you very much.
Thank you too.
Thank you.
Bye.
So now we are really coming to the talk about illustrating changes in time series data with data video, and the talk is given by Junhua Lu. So please play the video.
Hello everyone, I'm Junhua Lu from Zhejiang University. It's my honor to present our paper illustrating changes in time series data with data video. Showing the change over time is prevalent in data storytelling. Data videos, as a way to show the change in the data, have become increasingly popular. It is a compelling way for communicating data-driven facts to a broader audience. The left video uses animated bubble chart to show the change of global income and lifespan, and the right video demonstrates the growth of urban population of different countries with a bar chart race. However, creating a data video of time series which presents desired patterns is challenging. It is really laborious, and the authors have to switch back and forth between different steps. It also requires multiple skills, like data analysis, visualization, and video editing. Existing solutions have several limitations. Some tools suppose that the author already decides what insights to be conveyed in videos. In the case of time series data, the timestamps to be highlighted are selected before creating the video. However, this is not always the case. Some commercial software requires much effort of editing, or the expressiveness of videos is restricted by templates. To address these problems, we propose an approach which focuses on visually enhancing important changes in time series data with data video. The approach assists data video creation by better support of data exploration, automatic identification, and highlight for important changes with data mining methods, and providing flexible operation with visual effects to highlight them in the data video sequence. Here is the system pipeline. First, important changes are automatically extracted from the time series data and are visualized on the data timeline. Authors can view and explore them. Correspondingly, an editing timeline is provided to show how the visual enhancements that are applied to the changes on the data timeline. Authors can make modifications to both timelines. Finally, the video will be generated based on the editing timeline. The data used in our approach is two-dimensional time series data, which is ubiquitous. This type of data can be viewed as two tables, each for one dimension. For example, income and lifespan. Each row of the table represents time series of one item, for example, one country, while each column represents one timestamp. We use animated scatterplot to visualize the dynamics of data, and each point represents one data item. While showing the change over time with visualization is common, it is vague what does change exactly mean and what types of change are important and others are trivial. In our approach, we first segment the time series with change point detection, and then identify two types of important changes: drastic fluctuations and changes in the trend. Changes of the former type can be identified by checking salient peaks or valleys that are included in the segments, and segments whose slopes are significantly different with adjacent ones are regarded as changes in the trend. The change detection and segmentation is done by first compute the discrepancy between two adjacent windows that slide along the time series. Then, a peak search process on the curve finds those significant changes. Since there are two dimensions of data, we take the union of each dimension's changes. Besides the important changes of individual items, sometimes many items show changes simultaneously. For example, World War I leads to a huge drop in lifespan, as shown in the video. We regard this co-occurrence of important changes across different items as another type of pattern. We use the count-based method, which counts the frequency of each timestamp that appear in the important change segments, and find those timestamps with top k highest frequencies. In the line chart, there are three changes, which happens across 2, 3, and 4 countries, respectively. Timestamp 19 has the highest count, at which a co-occurrence of sharp drop happens among 4 items. Now let me introduce the interface, which includes configuration panel, exploration and editing panel, and editing widgets. Configuration view allows users to select the dimensions, data items, and the time span to be visualized. Users can also specify the number of segments and window widths, which is required by the change detection algorithm. The video length can also be set. Then click the button to generate the video sequence. After generation, the video is shown in the preview, and the sequence is shown with different timelines. Data timeline visualizes the detected important change segments with cyan stripes. Users can explore the changes in detail with the current time indicator. It has two modes. If all data items are selected, it will show co-occurrence patterns on the aggregation mode. Otherwise, It will show individual items changes in the individual mode. Users can also add new segments based on their own knowledge. Editing timelines are similar to those in video editing software, including speed and annotation timelines, and a timeline that displays important segments in correspondence to the data timeline. All these timelines are coordinated. We propose empirical rules to automatically apply visual effects to the changes. Besides this, we allow users to manually add visual effects, including annotations, zoom, and frozen frames. The system supports fixed position annotations and semantic annotations that move with data items in the same direction. In the use case, we use a dataset that is collected and compiled by Gapminder. It includes income and birth rate data of 203 countries from 1810 to 2018. After removing countries with too many missing values, there are 184 countries left. The user first selects the dimensions and interested countries. The time span is set as between 1900 and 2018. The window width and the number of segments are also set. Then the user explores the auto-generated interesting segments, which are automatically highlighted with a slow speed. She notices that the income and the birth rate of Japan fluctuated frequently between 1933 to 1957. The most notable changes happened after 1950. So she annotates Japan's income increased sharply while birth rate dropped dramatically. A similar drop of fertility happened in China during this time, and reached the lowest level in 1962. Based on her knowledge of history, she realizes that it was due to Great Famine and annotates this event. She keeps exploring the segments after the detected changes. She finds that China's birth rate was gradually decreasing from 1971 to 1992. She knows that this was due to one-child policy, and she slows down these segments using editing timeline and annotates this period. Finally, she exports the video. The system was assessed by 4 experts from a data journalism company in China. They used the system with Gapminder dataset and the China stock market dataset, and gave us some feedback. Overall, They were satisfied with our approach. They all commented that the interface is neat and well organized. They appreciated the idea of automatically extracting the changes and applying view effects, and then letting authors review and refine. Semantic annotation reduces effort of editing to track the movement of important data items. They also pointed out some limitations. Empirical role-based view effects may be unsatisfactory sometimes. If too many changes are detected, users may struggle to explore them one by one. And they also suggested that we can add the functionality of adding background music and voiceovers.
Thank you for your talk. A very interesting idea to support the storytellers. By providing an automatic system to detect events. So we have here one question on Discord, and it is, can somebody take the exported video and reproduce the chart?
Critical for the future of society.
So the video is stored as a JSON file. So we the story is organized as a JSON file, and we use D3 to render this video. So we can export the JSON file, and you can reproduce a chart.
Okay, then here's a very specific comment. Is it possible to detect negative impact of AIDS on African countries?
I'm not sure about that since I don't know about the data of like AIDS on African countries. Maybe you can like prepare data for me and I can run an example for you.
Another question here is whether your tool is online available and we can just borrow it and use it.
Currently, it is not available online.
Okay. Then thank you again for your talk. And we move to the next talk. And this is a talk about Nano for the public, an Exploranation perspective. And the authors are Gunnar Höst, Karljohan, Palmerius, and Konrad Schönborn. And the talk will be given by Gunnar Höst. So please play the video.
The public understanding of contemporary scientific issues is critical for the future of society. Public spaces such as science centers can impact science communication by providing active knowledge building experiences. In this respect, nanoscience and nanotechnology, or nano, is a domain associated with hope as well as fear. The significant impact that nano stands to make on humanity requires increased efforts for supporting public understanding of this area, with science centers central for doing so. In contributing to this mandate, we have previously developed NanoSim, an interactive simulation of nanoscopic properties, as part of an exhibition about nano. Based on the observation that rapid developments in visualization and interaction technology allow huge amounts of data to be visualized in public spaces, Huesmann et al. Have recently identified a new science communication paradigm that they term Exploranation, which combines explanatory and exploratory visualization approaches. While explanatory visualization is aimed to communicate scientific findings, exploratory visualization is employed by scientists through analytical tools that allow for interactive exploration of data, leading to scientific discovery. Although the exploration concept was coined recently, we opine that our previously developed interactive simulation, NanoSim, may contain multiple aspects captured by the exploration term. This initiated an objective to further reflect on the exploration concept to more rigorously specify the tenets that it may infer. In aiming to do so, we first describe a public exhibition aimed at visualizing Nano. We then present NanoSim, an interactive simulation of the Nano world, followed by examples of explorative experiences that may lead to learning with NanoSim. We then use this as a basis to offer further developments of the theoretical components that make up exploration, and consider how these can help inform the design and implementation of visualization in public spaces. We designed and developed NanoSim in the context of an exhibition titled Nano, which premiered in 2012 at the Norrköping Visualization Center in Sweden. The overall idea of Nano was to convey the nature and properties of the nanoscale and to highlight the often counterintuitive differences from the tangible macro world. Some exhibits aim to contribute to accessing highly abstract yet fundamental nanoscale interactions, such as simulating self-assembly of a virus capsid by physically turning a tombola. Embedded as part of the Nano exhibition, NanoSim was conceptualized and developed as an interactive visualization where visitors could gain access to nanoscale properties. In turn, such interactive experiences were envisaged as a conceptual tool for citizens to scaffold their assessment of the potential risks and benefits of Nano. NanoSim was designed to provide visitors with an interactive, immersive experience of the Nano world.
The display used is based on the 3D TV that renders 3D nano objects in front of the user. A depth camera is mounted facing downwards above the screen. This is used to adapt the graphics to the position of the viewer's head to produce correct perspective, natural navigation, and parallax effects, and to track gestures. A grab gesture is used to interact with virtual objects in the environment, sort of similar to pressing a mouse button, but in an immersive virtual world. In this first scenario, we see that at the nanoscale, the forces between nano objects tend to be sticky. In fact, nano objects can exhibit properties very different from observable matter.
By reflecting on the emerging paradigm of exploration, we have observed how the confluence of exploration and explanation is directly observable from users' interaction with NanoSim. We qualitatively analyzed 40 citizens' interaction with NanoSim during Think Aloud interviews. Consider the following example where the user describes how interacting with the rendered carbon nanotubes relates to interpreting communicated nano concepts.
Now I see that they are not, that they all go together might just be a random thing that happens. They might not be meant to be together, might be working one by one. That one understands differently when it's like this. Because when you move them, you just think that they all want to get into a group together. No.
The exploratory aspect offered by being able to grab, move, and interact with the nanotubes exists in combination with the explanation that forces between nanoscale objects arise when the objects are near each other by chance. Together, this sets the scene for conceptualizing processes such as self-assembly, where nanoscopic objects spontaneously aggregate through random encounters. We suggest that such episodes where components of exploration are simultaneously engaged are representative of explorative learning events. We now further elucidate these components.
As we've seen, exploration is based on the combination of explanatory visualization and exploratory visualization. We wanted to go beyond this definition and we wanted to find a way to conceptualize exploration that could provide a framework for assisting in the design of new interactive installations. So we went back to the original paper where Exploranation was introduced by Huesmann and co-workers, and we identified 3 underlying components. One of them is science communication, which can now be directly based on complex scientific data. And in addition, developments in visualization and interaction technology makes it possible to use the same approaches in both exploratory and explanatory visualizations. So these 3 components can then be combined in a Venn diagram. And in this diagram, Exploranation emerges as the intersection of these 3 components. From this simple diagram, we can also see that exploratory visualization can be represented by the combination of data visualization and interactivity. And combining the science communication component with either of the 2 other components gives rise to 2 different kinds of explanatory visualization. So the combination of data visualization and science communication could, for example, be an animation of scientific data, and the combination of science communication and interactive technology could be an infographic or an interactive model of a simple scientific relationship such as Newton's third law. So how could we use this conceptual model? We think that it might contribute to the work of developing and designing interactive installations by providing a framework for analyzing the requirements and potential issues that might arise in the development. To illustrate, we will give some examples from the development of the NanoSim exhibit. For the science communication component, designing for an exhibit for a themed exhibition made us aware of some of the contextual demands. A concrete example is the requirement for a certain space in front of our exhibit to allow users to interact with it. Another example is the requirement of matching the content in our exhibit with the overall story of the exhibition. And a related point here is the importance of considering the expected pre-knowledge of the visitors. In our case, this was quite challenging, given that nanoscience is such a complex subject. So we needed to find some everyday applications that the public might be aware of, and that was the reason for why we chose the particular scenarios that were included in the exhibit. In terms of interactivity, it has previously been pointed out by Huesmann et al. That the interaction interface needs to be both robust and intuitive to be useful. Designers should also consider whether the interaction across the exhibition could be made more consistent. Based on our experiences, we feel that the gesture-based interaction in 3 dimensions need to be further explored, since we found that users had trouble understanding how they were supposed to engage with the grab gestures. The gesture in itself was quite intuitive, but the problem was that it was hard for users to keep in mind that the depth camera needed to have a clear view of the circle that they formed when they made the grab gesture. Furthermore, data visualization aspects that need to be considered could be the mapping between the visualization that is shown and the underlying scientific concepts. One example from our case study is the use of the rubber band analogy to indicate the magnitude of the force that the user applies to a nanotube. It's also important to decide what visual modes that should be made available to the users. Each of the 3 components could also be further developed, and as one example, we have looked into the data visualization component by considering what kind of data that is being visualized and what consequences that may have from an exploration perspective. When it comes to the data visualization component, our case study uses data from an interactive simulation of moving objects at a nanoscale. So it represents dynamic computed data. And along this line, data could be characterized according to whether it is static or dynamic, and whether it is measured or computed. And this gives rise to a 4-field matrix of different kinds of data. And in this image we have inserted our case, which is the NanoSim, together with examples from the paper by Huesmann and co-workers. In this matrix, dynamic measured data is represented by astronomical data, which is being updated as new data sets become available. Static measurement data could be represented by medical imaging of CT scan data, for example, and static computer data, finally, can be represented by simulated molecular force field data. This kind of analysis may be important for the process of designing interactive exhibits, because the characteristics of the data visualization component will influence decisions in relation to the other components. For example, dynamic data may be more suitable for science communication related to processes and events, while static data may be suitable for communicating structures. So, in conclusion, we claim that computer dynamic data, as exemplified through the NanoSim exhibit, can be used to further expand the concept of exploranation. And we also think that further development of the three components and their interrelations should be done to better understand the theoretical principles and the scope of the exploranation construct.
Thank you very much for the talk. It just inspires you to try it out. So I really would like to check this out. One question that I have is, when talking about the explanation part and the science communication, is it necessary to have a guide there or domain experts that really supports this process, or can you leave somebody alone just with some
In this
notes on the
presentation,
screen
I will
or
describe a system we created.
explanations on demand?
Thank you, and thank you all for listening. I think that's a great question, and I think that you could go in multiple ways. A guide could be a very useful complement, but you could also try to get a self-sustained system, but that's a challenge for sure. You need to get people to understand what they are supposed to do in perhaps 5 seconds or something like that. So it's a challenge.
So in your example, you kind of combined this computer screen where they could interact together with also having a physical artifact there. How important is kind of this combination, or does one thing just run by itself?
Yeah, Konrad?
Yeah, I think that's one of the sort of ultimate questions. Especially in a science center setting, where you really want to, first and foremost, engender interest in science. And really one way of accessing abstract phenomena is perhaps using bodily experiences as a way to bridge and to actually access things through bodily interaction that we otherwise cannot perceive in the macro world. So this is where a combination of virtual objects together with bodily movements is an extremely exciting premise to move forward in public settings.
Okay, thank you. So did you, for your exhibit, kind of measure how long people stayed with the exhibit? How long could you engage them with your different things that you showed?
Another really fantastic question, and also at the crux of modern and contemporary research in this area, is to actually measure interaction. What are citizens and users actually doing with the system? And then how can we link these patterns with what sort of conceptual construction or learning that occurs?
Okay, thank you very much. I think we have to move on and go to the next talk. And this is again about public engagement. It's called Pixel Clipper, Supporting Public Engagement and Conversation About Visualization. The authors are Jagoda Walny, Sarah Storboom, Richard Pusch, Stephen Munsu Wang, Sören Kutzen, Shilak Carpendale, and Wesley Willett. And the talk will be given by Sarah. So please play the video.
In this presentation, I will describe a system we created called Pixel Clipper. It is a tool we built for facilitating public engagement with data at events. It supports data-driven conversations through the expressive capture and annotation of parts of a data visualization, and by using these captures to engage people and stimulate dialogue. We created Pixel Clipper within the context of a multi-year project. Lots of people in our lab were involved over the years. Our goal was to make open government data not only available, but also accessible to Canadians. We designed a set of 4 data visualizations in collaboration with the Canada Energy Regulator, or CER. With these visualizations, the challenge is that they can be quite complex. When designing them, we were not able to present them with much guidance or editorial filters. This is because presenting any particular point of view takes away from citizens being able to form their own conclusions using the data. When engaging citizens with open data, we need to balance neutral presentation with support for people to be able to interpret it. One way we found to address this challenge was to hold in-person events in publicly accessible spaces. Data experts who work with the data on a regular basis are at the event to provide answers and guidance about how to navigate and learn from the visualizations. Before developing Pixel Clipper, we found presenting in a public context usually resulted in a facilitator-led model. Facilitators would guide visitors through set views in the visualization, and visitors rarely had an opportunity to interact with the visualizations themselves. We wanted to bridge independent exploration and facilitation to create a more engaging experience for visitors. We think about engagement as a spectrum on 2 dimensions: direct engagement with the space, artifacts, and people, and engagement with the content itself, which in our case is the data depicted in the visualizations. Our first goal was to have our event be livelier and more approachable by supporting multiple degrees of direct engagement. This means providing experiences for passive engagement, like listening to someone talk or being presented with images, and active engagement, such as face-to-face dialogue and activities. We also want to support a return experience with artifacts that support continued sharing and dialogue. Our second goal is to support engagement with the data across the spectrum. Some people will be satisfied simply knowing that the data exists, while others will want to explore the data more thoroughly, and those who are highly engaged will form their own conclusions and questions around the data. We want to meet people where they're at with the data and to support their transition along the spectrum. Our final goal is to empower individuals to explore the visualizations themselves and to better support the facilitators' meaningful engagement with visitors. Our solution, Pixel Clipper, is a tool that allows for the expressive selection of parts of a visualization and a set of display programs that use the clippings to engage visitors at different points along the spectrum. The expressive selection tool is inspired by the analog act of cutting out clippings from magazines or newspapers to save specific pieces of information. Our digital version is in the form of a browser extension. When it's installed, it appears on the pages of the Canada Energy Regulator visualizations without impeding interaction with them. Clicking the Create button allows for a quick and gestural selection of parts of the visualization along an overlaid grid. The person interacting can express themselves through visual selection and text by leaving a comment and attribution. Their clipping links back to the exact same view of the visualization using a unique URL. The browser extension will also show all clippings made at the same visualization view. This makes it so you can see other visitors' contributions while browsing the visualizations. From the browser tool, clippings are stored in a database, which can also be retrieved by other components of our system, like this ambient display, which is designed for a large screen that is not interactive. Its purpose is to attract potential visitors through passive engagement. It reveals clippings in an ongoing animation that is intended to capture attention and create curiosity around the data. The order of clippings is semi-random, prioritizes new content, and displays facilitator-created content at regular intervals. When facilitators use the tool to create clippings, we would tag these and they appear with the maple leaf icon. The facilitation interface supports conversations between data experts and event attendees around large, touch-enabled displays. The left side shows fully interactive visualizations, and the right side shows the clippings and comments. If a clipping is selected, the frame on the left loads the view of the visualization where that clipping was taken. The selected clipping is presented in the top right and is added to the selection history list. This display also allows facilitators to demo the visualization and respond to clippings created by the public. The website is a mobile-friendly display of all clippings in the database during and after the event. It provides links to the homepage of each visualization, information about the project, and directions for installing the browser extension. Visitors can filter and search through the visualizations to find specific ones or simply browse. The site supports sharing with the clippings on Twitter and will open the visualization if selected. And again, it opens to the exact place where the clipping was made. We were able to deploy Pixel Clipper at 3 events. They were modestly advertised, but primarily we were aiming to attract people passing by, so we set up in busy public spaces. The first was a pilot event, held in our university library, where we deployed an early version of the system, which informed the development of some of the components I mentioned, as well as the layout of our event spaces after. The next events took place at the Central Public Library in Calgary. Both were in collaboration with other organizers. The first was a Faculty of Science showcase, and the second was led by the Canada Energy Regulator. Our configuration of the event setup considers the implicit division of space created by the arrangement and orientation of furniture and displays. Also, where people tend to gather and rest. As you can see in the middle photo, we try to open up the space by orienting displays in different directions. Components that support passive engagement are placed at the perimeter of the space. This is seen on the right, where the ambient display is placed near a casual seating area to capture the attention of someone lingering here, or as a place to retreat and reflect. We position the facilitator displays in a central position where they can support both passive and active engagement. This space supports people who might be encouraged to explore on their own after an introduction to the visualizations, those who have already made a clipping they want the facilitator to address, and those who are satisfied with a facilitator-led experience. We also placed multiple computer stations in the space. People could use them to interact with the visualizations, make new clippings, and explore the other clippings using the website, which we set to the homepage. We used both standing stations to allow for low commitment interactions and seated stations for comfortable, longer-term browsing and exploration. These stations support all 3 of our design goals at the highest level because they give visitors explicit permission to explore the visualizations on their own, and because the Pixel Clipper tool gives them explicit permission to express their questions and observations in a personalized way. We also made the extension publicly available so individuals who had their own device could download it. The website also supports passive engagement during the event because visitors can scroll through clippings on their mobile device. We advertise the website using a short URL in various places during the event, as well as on physical artifacts that visitors could take with them for future return. Because Pixel Clipper is designed for in-the-wild events, there are many complicated factors that limit our ability to fully understand the impact of the Pixel Clipper system. In comparison to other demos we have run, however, we notice that visitors are engaged for longer, sometimes spending 30 minutes or more at a station, exploring the visualizations and creating clippings. Clippings created at the event, some of which you can see here, are themselves artifacts of direct engagement and engagement with the data. As designers, these give us some insight into some of the criticisms and sometimes very personal reflections on the data. In the paper, we discuss more of the challenges and opportunities we found with Pixel Clipper.
Overall, however, we feel that the system showcases the potential of an expressive clipping and commenting tool to create new entry points into visualizations. It provides viewers with ways of contributing to data-driven discussions along the spectrum of engagement. It also illustrated how dedicated facilitator and ambient displays can leverage these contributions to support rich, in-person conversations and create interest. Based on our initial experiences, we think that this tool holds considerable promise and might support public engagement with a range of data sets. They could even serve as building blocks for a wide range of systems that bridge online and offline discussions around data. Thank you.
Thank you for sharing with us your experiences with Pixel Clipper here. I have a question concerning kind of the time that they spend, people that they are engaged and involved with your tool. You mentioned that they spend a lot of time there.
My name is
So
Alejandro
how
Benito
much
Santos.
time
I'm
do
a
they
research
spend
assistant and
exploring
PhD
what
candidate
other
at the
people did, and how much of the time do they create their own new stuff?
Oh, that's a really good question. And the answer is I don't know, actually. And also that they can kind of do both at the same time when the tool is installed, because I think you saw in one of the videos there, it sort of overlays over top of the website, so they can be exploring and they can also see what other people are contributing at the same time. So yeah, very hard to distinguish.
So here's a question in Discord. Were the design considerations around accessibility, for instance, did you look at ways for interacting with the visualizations with different levels of mobility, vision, visual literacy?
Yeah, that's also a really good question. I would say our system itself is somewhat limited in that way. The visualizations themselves that are on the website, on the NEB website or CER website, they are fully accessible and they can be sort of read aloud and uses all kinds of accessibility. For us, mobility was a big one because actually those visualizations themselves don't work very well on mobile. So we were noticing that even people who were passing through our event, if they couldn't stay, there wasn't really a way for them to sort of like follow a link and then, you know, browse those things on their own time. So actually having a website showing those clippings was enabling them to engage in some small way through mobile, which wasn't an option with the visualizations we were dealing with.
Okay, thank you. So there's another question about how you envision this work during COVID when public events are not common.
Yeah, actually, that's a good question. I hadn't thought about that. But there's actually a lot of opportunity for it, especially in terms of, you know, these public stations maybe not such a great option where people are kind of like coming to these kiosks and interacting. But we made the tool available for people to download on their own devices. And so you could imagine, you know, distanced people on their own devices interacting with this, and maybe in a sort of a theater setting or something like that, where there's a facilitator, like that's totally possible and doable. And it also allows for a lot of conversation to happen completely remotely using that, just the sort of artifacts on the side as you're browsing and being able to see what other people are doing. And by nature, it's you're able to create conversation, because if you take a clipping out of view, then it shows like in a sort of order next to that view, and so you're able to kind of create dialogue that way too. So yeah.
Okay, thank you again for the interesting talk. And then we move on to the last talk in the session. We switch a little bit the topic. It's about a data-driven introduction to authors, readings, and techniques for visualization in digital humanities. And the authors are Alejandro Benito Santos and Robert Teron Sanchez. And it will be presented by Alejandro. So, welcome to the talk.
Thanks for the introduction. My name is Alejandro Benito Santos. I'm a research assistant and PhD candidate at the University of Salamanca in Spain. And I'll be presenting my work, a data-driven introduction to authors, readings, and techniques in visualization for the digital humanities. There was a CG&A paper that was published this year. So we'll be discussing mainly visualization for the digital humanities, which is a type of interdisciplinary collaboration, which involves domain experts who are the humanists and visualization experts who assist them with their problems using their expertise on analysis techniques and visualization algorithms. So it presents common elements with other kinds of interdisciplinary collaborations, such as VIS or sports piece, but it also has many other features that make it quite unique. And this is probably the reason why it has gained popularity among the VIS community in recent times. So a good example of this is the celebration of the VIS 48 workshop, which is a collocated event to this conference, and that hopefully just had its 5th edition celebrated. Well, it turns out that the digital humanities are an exciting field of experimentation for visualization researchers, mainly because sometimes the data sets are rich and unexplored. So you are probably facing some data that was just freshly digitized from the originals that were sitting in a library for years. And also, the digital humanities and social sciences sometimes or very often pursue different aims to those of other disciplines that are commonly supported by visualization, like the experimental sciences. So this provides new ways to explore new visualization approaches and evaluation techniques. But these good parts are also the same ones that make it also quite challenging at some point. So, for example, this lack of evaluation techniques makes it challenging to create valuable research, visualization research sometimes in this collaboration. And also a problem is that the discipline is quite fragmented. So you have people discussing visualization design at the DH conferences who are not the same people who come around these circles. So this reflects still a large gap that there is between computer scientists and humanists that well, luckily is starting slowly to change. So our study departed from a set of open questions that were laid out by the organizers of the VIS 48 workshop. So concretely, we focused on those that were meant to provide an answer to digital humanities scholars willing to get involved in visualization research. And we also added a third one that was about removing obstacles for visualization researchers who were willing to get involved in digital humanities research. That could be me 5 years ago, or maybe senior researchers who are coming from other types of this practice, and the collaboration might seem challenging for them. So the objectives of our work were to provide an overview of the discipline, surveying the topic according to its topics and publications and authors, and also enable comparative analysis that allowed to measure the differences between the two sides of the collaboration and also these two communities and the rest of the visualization research. And also probably open up new collaboration ways by identifying people with or other potential colleagues with similar interests. So concretely, our contributions were a normalized dataset of VIS-48 and DH4VIS publications and related works that were extracted from reference lists, and also a bibliographic analysis on this data that we'll explain in a moment. So we departed from a seed dataset of relevant publications of people who identify themselves as working at the intersection of visualization and digital humanities. So the way we went about this is that for building the dataset, we polled two main venues. So this was the workshop on visualization for the digital humanities, which I already mentioned, and also the conference by the Alliance of Digital Humanities Organization, which is the biggest digital humanities conference in the world, and its associated journal, the Digital Humanities Quarterly. So for obtaining publications in the visualization site, we extracted, we went to the VIS-48 workshop and extracted, apart from authors' names and publication years, etc., we obtained the author assigned keywords to conduct the second part of the study. Obtaining the publications from the DH site was slightly more difficult, so we had to go to the TI files, and we ran a regularized patient to catch the intention of the authors to use visualization in their work, or to have it as a first-class citizen in their research. So, for example, we matched those publications by looking at their titles or lists of keywords and topics. So in the end, we obtained 276 publications, and we extracted cited works from the long papers. So from this references dataset, we performed frequency analysis of publications and also a temporal analysis. And from this reference, from a subset of this references dataset, we extracted also author-assigned keywords, and we conducted a frequency analysis on them, and also a concurrence analysis that has been used in the past by other visualization researchers to characterize visualization research. Okay, so these are the results of the quantitative analysis that we performed on the data. So they gave us like top-cited papers and books. But rather than being understood as popularity rankings, we believe that they should be regarded as entry points to the discipline for novel researchers. And also there are many other sub-themes that are worth being explored. So the temporal analysis that we conducted on the citations looks quite similar in both sites. Slightly off, or slightly more recent work is cited by the visualization community, but nothing big. So finally, we went to perform analysis on the keywords to identify the themes and how these themes related to each other. So here you have the distribution of keywords, which is follows a power law, which is very common in these cases. And the top 20 most used keywords in this case were represented the major DH themes, such as text visualization, GIS, or mapping and networks. But also two major concerns of VIS-48 appeared. So this was the evaluation and collaboration. And also, surprisingly, uncertainty appeared amongst these terms, which could mean that these people are citing words that discuss uncertainty, but they don't use it in their own paper. So this means that uncertainty is a big concern for them, but there's little research on the field performed on uncertainty. Okay, so we compressed the data to perform the cohort analysis. This meant that we related themes that shared stems. We did this to avoid us to have to perform a manual coding of the keywords, and the approach has certain downsides, but it's good because it's reproducible, and it worked well for us in this case. So analyzing these stems, we can see that also they are similarly distributed to keywords. So they also resemble a power law distribution. So we went ahead and conducted a cohort analysis. So the cohort analysis departs, it follows the method proposed by Eisenberg and her colleagues. It departs from a term document matrix. So from this term document matrix, we built a concurrence analysis of keyword tokens. In turn, they were hierarchically clustered using Word's method and square Euclidean distance. And from here, we built a keywords network in which the edges show positive correlations between nodes, and also a strategic diagram and a keywords network, a pruned keywords network that's presented at the end of the study. So these are the results of the strategic diagram. So here we can see many familiar topics to the digital humanities community. So we have, for example, some bigrams reproduced here in this cluster. So text mining, for example, or literary studies, or semantic link web, etc. So we calculated the density and centrality of these clusters in the network, and we plotted it in a strategic diagram. So we can see here, for example, that natural language processing is very dense, because it appears apparently many times, and these terms are highly correlated. And also to the right of the chart, we can see certain topics that are quite central. So, for example, this would be cultural collections and literary studies. So if we go to the network that was built after that, we can see also these clusters represented in a network. So we can see how these things relate to each other. So we can see the general topics that we saw in the previously, like topic models and social networks on the right, but also there are certain queries associations like medieval alignment and dynamic programming that could be interesting to explore. Also, we can see at the center semantic link web and natural language processing, which are related with text mining and word embeddings that are in turn related to automatic feature extraction and terms related to that. So we hope that with this diagram, the user or the readers of our paper could get an impression of what generally the digital humanities and visualization is about. So in future work, we are planning to make updates to this dataset, like we did in the VIS for the H workshop, and also we are willing to cross it with other problem-driven visualization research, and this was demonstrated in a paper that is also presented at this conference. Okay, and that was it. So thank you very much. I hope that you found that interesting.
Oh, thank you for this talk. I think there's an interesting approach to bridge the gap between the visualization and another community. What do you think? How easy is it to transfer your idea to another application domain?
Well, I think it's really hard. It's something has been puzzling me for some years already. And I think that especially the visualization practice with digital humanities is very challenging because what I mentioned in the presentation, that the aims of the humanities are radically different from those of the experimental sciences. So much part of many times it occurs that digital humanists are not looking for definite answers, but rather they are looking for insight that leads them to make better and more questions. So I think this particular kind of practice is very challenging, and this is something that I've been studying for some time already.
Yeah, something that I would be interested in, when you inspected all these keywords, how often did it happen that a keyword only appeared once or twice?
Well, that appeared a lot, I think. But the main aim of these diagrams and the network that I built in the end is to give an impression or of a general picture of the topics. So the keywords that appear on the network in the end, they appear more often. So because they are also filtered, but by a threshold. So I think there was 7 times at least they need to appear in order to get promoted to that chart. But there are many sub-themes in the dataset that we composed that are not, I think, less important than others, and they deserve to be explored because they offer, I think, many potential ways of collaboration, of future collaborations to advance the field.
Probably a last question. So did you consider to extend your analysis to the entire abstract, not only to the keywords that the people have chosen themselves?
Yeah, this is something that I've been considering for some time already, and I decided, well, I think the author-assigned keywords have granted knowledge by the authors that cannot be reproduced by automatic means, just by running an algorithm to extract key phrases or keywords from the abstracts themselves. This is something that I think it's an developed research area, and but I advocate for the use of author-assigned keywords and the study of these keywords, because I think they are very useful to drive the exploration and to build some more tools like visual text analytic tools, like the one I'm presenting in a short paper in this conference. That's well, I think it's worth exploring.
Okay, thank you. I think we have to come to an end. So we have been asking too much in between. So I would like to thank all the speakers of the session again. I think it was a very interesting session, and I wish you a nice evening or whatever time it is in your time zone. Okay, bye.
See ya.
In this study, we designed PassVisor to fully analyze the passing dynamics. Users can hover on a pattern diagram to see all the passing patterns, its characteristics, and how these patterns distributed over phases. They can further click on a pattern to see its phases, select one phase to see the passing, and inspect the prior statistics during passing.
We present 3 external labeling concepts that allow a user to browse through point sets without the need of zooming in and out. In the first method, labels are distributed on multiple pages. The next method arranges the labels in a single row that can be continuously slid along the bottom side of the map. In our third method, labels are distributed on stacks, which a user can independently browse through.
When doing the cell division for an embryo, plant biologists use several tools to get segmented 3D dataset and build the hierarchy tree manually by traversing and analyzing neighboring cells and deciding on which neighbor is the sister based on their knowledge. In this poster, we present an interactive system for biologists to help with analyzing the development of plant embryo.
This work presents a detailed account of an attempt to explain tightly coupled relationships through storytelling and animation in a multi-user, informal learning environment to a public with varying prior knowledge on the domain and identifies lessons for future design. It offers qualitative empirical findings with particular emphasis on how, despite careful design, visitors may walk away with little knowledge about the data and the problem.
We present the visualizations for the Red Sea AD simulation ensemble available on the VIS Contest 2020 website to analyze the commonalities and differences in the AD features observed across the ensemble members. Specifically, we demonstrate the applications of statistical visualization techniques in the context of volume rendering, mass complexes, and isocontours to gain insight into the potential AD positions and their spatial uncertainty for the ensemble.
Kirigami is a rich, complex Japanese tradition of paper cutting. We leverage kirigami to create new physical data representation and simple interaction. This is an example which shows global warming in 5 countries. The expansion shows mean temperature in each country in 1962. The user can manipulate the model by adding measure weights, and the increased expansion shows the mean temperature in 2012.
This paper explores the efficacy of using narratives as a medium of explaining the causality in causal networks. Now, towards this end, we provide you a glimpse of CauseWorks, a causality visualization system for generating narratives given a set of interventions and objectives for a causal model. And we further validate CauseWorks through interviews with experts. Please read our paper to know more. Thank you.
The blood vessel structure on the human placenta can be an important indicator in the detection of birth complications, but the segmentation of the vasculature tree remains a challenging problem. In our work, we show how MRI visualizations in immersive virtual reality can help medical practitioners to identify blood vessels without the need for a contrast agent. We present the results of a user study and lessons we learned for vasculature exploration in VR.
Hello, we are presenting deep volumetric ambient occlusion, a novel technique for deep learning-based ambient occlusion in volume rendering. In our talk, we're going to discuss 3 things. First of all, volume-to-volume learning in general. Second, how you would combine unstructured information with 3D CNNs. And lastly, what you can take away from our work for volume learning in general. See you there.
We present an investigation into design judgment in data viz practice. Our findings show how different types of judgments influence design decision-making. Our findings also show that judgments occur in complex and layered ways while designers move through their process. We discuss implications for future research and pedagogy.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Data GIFs are enjoying increasing popularity on social media as a format for data-driven storytelling with visualization. Simple visual messages are embedded in the short animations and are played in automatic repetition. Here we present a structured design space and a set of design instructions to create effective data GIFs.
It takes a large amount of time to load all the point data for many distant point clouds in a virtual and augmented reality space. An appropriate amount of points must be displayed at an appropriate size according to the distance. We propose visualizing point clouds by progressively voxelizing them with different resolutions to solve these problems.
We conducted semi-structured interviews with 20 data viz practitioners to investigate how they understand ChartJunk and the factors that influence how they use it in their design work. Our findings suggest a number of themes about each topic. We highlight the personal and situated nature of how practitioners understand and make use of concepts, and argue for more practice-led research within VIS.
Data journalists are a compelling group through which to study data wrangling because they frequently publish their methods to sites such as GitHub. In Table Scraps, we perform a qualitative study of their codes and computational notebooks to better understand the needs and pain points of journalists while data wrangling. From this data, we produce 2 taxonomies of computational journalism and a framework for multi-table data wrangling, and demonstrate these contributions through 2 case studies.
Studies in HCI follow similar steps in explaining hypotheses, laying out a study setup, and reporting results. Many of these decisions are buried in dense scientific text. We contribute a set of examples of how data comics support that reporting, providing an initial set of concrete ideas for how to communicate common stages of HCI studies and statistical analysis.
Scatterplots maps are popular. However, we have better encodings for numeric values. Check out the prism map. Worry about occlusion and perspective distortion? Let's go immersive. Want to have both of them? We present tilt map, a novel interaction technique for transitioning from a Scatterplots map to a prism map to a bar chart to overcome the limitations of each. Believe me, tilt map opens up many research possibilities.
We present a suggestive interface for untangling mathematical knots with complicated structures. Our interface can help users deform knots with the right sequence of mathematically legal moves. It allows one to sketch and untangle knots by proposing the right method moves. If interested, welcome to our presentation.
Typically, black hole visualization takes a lot of compute time, but we achieve a quite faithful reproduction at interactive rates on a standard computer. For this, we make use of a novel adaptive grid approach to focus calculations where needed. Coupled with filtering and interpolation methods, we can obtain high-quality imagery. Our approach accepts star catalogs and environment maps and generates the resulting deformations in real time.
Hey everyone, I'm Junhua Lu, PhD candidate at Purdue University, computer graphics major, and presenting our recent research outcome, Phoenix Map, an abstract approach to visualize 2D spatial distributions. Due to the conflicts between the limitation of display area and the large amount of comparative distributions need to visualize, the current methods are always restricted. These observations encourage us to come up with a solution by abstracting the visualization.
MetroSets is an online platform for visualizing sets as metro maps. In this style of drawing, sets are represented with metro lines, while the elements they contain are represented as stations. MetroSets is implemented using a modular 4-step pipeline, with a variety of choices for each step. The final visualization is interactive, with support for all common set operations. MetroSets is fully implemented and can be found at the displayed URL.
To uncover football tactics, we create spaces and times. We use time query, construct spaces, construct times. Our approach was used for reconstructing team tactics in different classes of game situation. Our domain experts are happy, and the Germans shall win again and again.
Designed in response to the COVID-19 pandemic, the novel visualization technique we are calling GOWNS accommodates continuously incoming and increasing case data without distorting past data. Layering linear scale graphs shows both small and large numbers. This allows more detail to be seen when scrubbing through time and comparing regions by realigning the GOWNS based on case numbers.
We study the limitations of node-link diagrams with respect to pathfinding tasks. But wait, I hear you say, hasn't that been studied before? Actually no. Path studies typically measure only accuracy and time for fixed network sizes. We used a number of physiological measures, including brain activity, and looked at a range of network sizes and densities. We discovered that the threshold for difficulty is much lower than expected. This talk is essential viewing for anyone interested in network visualization design.
Visual data analysis of large amounts of data demanded solution which provides users the means to enter into the dialogue with the information visualization. To understand how multimodal interaction using touch, speech, and middle hand gestures can tackle this gap, we conducted an explorative interaction elicitation study. We argue that users are highly receptive to use multimodal interaction for visual data analysis and that especially the combination of touch and speech would be promising due to their complementary nature.
We present an exploration into co-located collaborative immersive analytics in a prototype called Fiesta, the free-roaming immersive environment to support team-based analysis. The prototype allows groups of users to visualize and explore their data in a room-scale environment, which we used in an exploratory study involving 10 groups of 3 participants. We focus on the roles which 2D surfaces have, as well as how users leverage the 3D space during both the individual and collaborative work.
Although prior work has examined how visualization impacts decision-making, there is no concrete method for quantifying and comparing the impact of different encodings on decisions. We rethink how we evaluate decision-making with visualizations by leveraging work from economic theory. We present the results of a large-scale lottery game that evaluates the impact of 5 different visualization designs on risk behavior and decision-making.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Urban motion, illustrating the movement of population from billions of sparse trajectory records. Chang'an Avenue correlates with movement flow, the regions with the largest flow volume. Zoom into the region. The southern Huilongguan region is mostly in blue, cut by G6, which could account for its commuting issue. Rainstorm in Beijing, movement speed is much higher on average. At the remote regions of Beijing, there are few local movements.
Many real-world analysis environments involve multiple types of experts and analysts working together. We aim to provide new knowledge about